Hello. In this video we're going to talk about zeros of polynomial functions, and we're going to talk about different methods or different tools that we can use in order to figure out the zeros of a polynomial function. And at the very end I'll go over a summary kind of showing a graph as to how to understand zeros of polynomials better. Before we begin, let's recall that zeros of a polynomial are the x values that make the polynomial equal to 0. If you're looking at a graph, it is where the graph crosses the x-axis. Something to keep in mind, and I think is very important to understand because later on we'll try to explain it under this light, is that the zero product principle helps us understand polynomials in some way. And so what is the zero product principle? If you recall, it is the product of two or more polynomials or algebraic expressions. If that product is equal to 0, then at least one of the factors has to be equal to 0. So for example, if we have the product a times b, and all of that is set equal to 0, then either a has to be equal to 0 or b has to be equal to 0 at some value. Okay, and so think a and b are larger algebraic expressions, then we would be looking for a value of x that makes that equal to 0, and so on. When finding zeros of polynomial functions, you may be wondering, what types of numbers can you expect? Right? It's a fair question. So for example, here we have a polynomial f, and it is equals to x plus 5 times 7x minus 1 times x minus the square root of 3 times x minus 6 plus 2i and the last term. So if you set this equal to 0 and use the zero product property, we get that one of the zeros is -5. Another 0 will be 1/7. The other 0 would be square root of 3. The other 0 will be 6 minus 2i and 6 plus 2i. And as you can see, it's been broken down by type of number. So -5 and 1/7 are going to be considered rational zeros, right? The square root of 3 is an irrational number, and together they make, well, they don't make, they're part of the real numbers. So those are considered real zeros. Here we have the two complex imaginary zeros, and those fall under the non-real zeros. Okay, so to answer the big question, what type of zeros can you expect to find? Well, anything, real and non-real. So complex numbers, real numbers, any type of number that we know can be considered a zero in a polynomial function. Okay, so with that in mind, let's move on. Now let's talk about the rational zero theorem. So what is this? The rational zero theorem allows us to create a list of possible rational zeros. So this is very important. You want to know that this only gives you a list of possible zeros. It doesn't give you the list of all of the zeros. So in other words, just because you have a list doesn't mean that all the numbers that you just found are going to be zeros. So this is important, right? It's just the possible list of zeros. Now, not every number in the list is a zero, like I just said, but every zero of the polynomial will appear on the list. Okay? Then, here's the definition, the more textbook definition. So if you have a polynomial of this form, that has integer coefficients, and you create this ratio P over Q, where P over Q is reduced to its lowest terms, then we have a rational zero of f. If then P is a factor of the constant term a sub 0, so the last number by itself, that is the constant term, and Q is a factor of the leading coefficient, which is this first number in here. So that is the textbook definition of it. Let's move on and do an example. To use the theorem, you want to do a list of all the factors of the constant term, and then you want to list all of the factors of the leading coefficient. Then you're going to create a ratio between those, like we're showing here. So all of the possible rational zeros is nothing but a factor division between the constant terms, a sub 0, or, well, divided by the factors of the leading term, a sub n. So here we'll do an example where we want to list all the possible zeros of this polynomial. The polynomial is f of x equals to negative x to the fourth power plus 3x squared plus 4. So I like to do it this way, where I just, for example, say P is the number 4. Okay? And I'm going to list the factors of 4. So 1, 2, and 4. Now keep in mind that here we have to list all of the possibilities. So notice that 1 times 4 is 4, 2 times 2 is 4, 4 times 1 is 4, but then also the negative version of the numbers. So you have to consider the plus and minus version, right? What I'm saying is negative 1 times negative 4, negative 2 times negative 2, and so on. That will give us positive 4. Okay, and then Q is the number negative 1. Well, what are the factors of negative 1? Well, it's positive and negative 1, right? So then we'll do P divided by Q, which means all of the factors that we found divided by 1. So I guess we'll write them out just to get an idea of what we're doing. So we'll get a list like plus or minus 1. So in essence, right, you're doing plus or minus 1 divided by 1. So we'll do it just for purposes of showing the example, but you don't have to do it like this whenever there's a 1 in the denominator, because it's understood that you don't have to put a 1 in the denominator. So the list of possible rational zeros is going to be this: plus or minus 1, plus or minus 2, and plus or minus 4. So from that list, the zeros of the polynomial f are here. They are in this list. Which one are they? We don't know yet. Let's do another example, and this one is going to be same exercise as before, where we're listing all the rational zeros of the polynomial f of x, which in this case is 15x to the third power plus 14x squared minus 3x minus 2. So let's go ahead and do the same thing, where we are listing the different factors. So P in this case is negative 2, and its factors are going to be plus or minus 1, and then plus or minus 2. Q is going to be positive 15. So the factors of it are going to be plus or minus 1, plus or minus 3, plus or minus 5, and then plus or minus 15. Okay? Now, we're going to do what we did. Well, we're going to use the definition, right, which is the possible rational zeros is equals to all of the factors of the constant term divided by the factors of the leading coefficient. So P over Q is going to be plus or minus 1 plus or minus 2 divided by plus or minus 1 plus or minus 3 plus or minus 5 and plus or minus 15. Okay, so this breaks up into plus or minus 1. So 1 divided by 1, 1 divided by 3, so it's going to be plus or minus 1/3, then plus or minus 1/5, plus or minus 1/15, okay, and then plus or minus 2, plus or minus 2/3, plus or minus 2/5, and then plus or minus 2/15. So we have 1, 2, 3, 4, 5, 6, 7, 8 different possible rational zeros. Well, I lie. There's 16 of them because it's the plus or minus version, right? You have positive 1, negative 1, positive 1/3, negative 1/3, and so on. So these are the possible rational zeros, right? Hopefully this makes sense and it's a good example as to how to find all of the possible rational zeros. Next, this is a more hands-on problem. We're trying to find all of the zeros of the polynomial f of x equals to x cubed plus 2x squared minus 5x minus 6. Let's go ahead and get started by listing all of the possible rational zeros. Once we've found the list of rational zeros, we need to check which of those actually works by doing synthetic division and trying to find a remainder of 0. So let's check the first possible rational zero. We'll do 1. So positive 1, we're going to see if it goes as a possible rational zero. That gives us 0 as a remainder. So we're going to put the coefficients of f of x here. And then we're going to do synthetic division. We see that by trying the value x equals 1, we get a remainder of negative 8. So 1 is not a rational zero. We have to try another number. So another possible 0, we can do positive 2. So positive 2 as in like the value of x equals 2, seeing if it goes into the polynomial f of x, and we get a 0 as a remainder. And we see that x equals 2 is a0 of the polynomial f of x. So what does that mean? Well, what we can do is rewrite f of x in the following form. And so x to the third plus 2x squared minus 5x minus 6 is the same thing as x minus 2, which comes from this factor here, right, which is x equals to 2, and that multiplied to the quotient that we found here, the 1, 4, 3, those are the coefficients of the following polynomial. X squared plus 4x plus 3. And now all that we have to do is refactor whatever is left over. So we can factor this polynomial by doing quadratic formula, or just by saying, what are two numbers that add up to 4 and multiply to 3, and I'm pretty sure it's going to be 1 and 3. Okay, so once we do that, we have now factored it linearly, because now everything has a power of 1 at most, and if we set this equals to 0, we get the following. We get that x minus 2, x plus 1, and x plus 3 all multiplied to each other give you 0. And if we use the zero product property, it is the case that we know that x equals to 2 is a 0 of the polynomial, but now we also get x equals negative 1 and x equals to negative 3 as a solution. Okay, so this is a solution set for that polynomial. Now let's talk about some properties of the roots. Okay, now if a polynomial has degree n, right, whatever the highest degree of the polynomial is, counting multiple roots separately, the equation is going to have n roots. Okay, like we saw in the previous example, it was a degree 3 polynomial, and we found 3 solutions for it. So that means that whatever the power of the polynomial is, that's how many roots you could potentially have. Okay. The second property that we want to talk about is if the polynomial has complex roots. So for example, if a plus bi is a root of the polynomial, okay, with b not equal to 0, meaning that we have a fully complex number, not a real number just by itself, then the imaginary number a minus bi is also a root. So notice that contrast. You have a plus bi, so it's a given that a minus bi is also a root. It just tells us that imaginary root happen in conjugate pairs. Okay, it's like a freebie. If you know that you get one complex root as the solution, then you can automatically assume that its complex conjugate is also a solution to the polynomial. A very important thing in mathematics is this fundamental theorem of algebra, and it just tells us that, pretty much describing the previous property that we talked about. So if f of x is a polynomial of degree n, where n is greater than 1, greater than or equal to 1, then the equation f of x equals to 0 has at least one complex root. It's just a definition, and what it means is that we can expect at least one complex root, meaning a real number or a complex number. So it's just an extension of the properties that we talked about previously. Not much else to say about it. Okay, so don't get confused with, because it says a complex root, does that not include real numbers? It does. Okay. Now let's talk about the linear factorization theorem. So like we saw in the previous example that we worked out, we were able to get it in product of small factors, right, to make up the original polynomial. So what the linear factorization theorem tells us is the following. So if you have f of x as the standard definition for a polynomial, where the highest power n is greater than 1, and the leading coefficient is not 0, then you can rewrite this polynomial as the following. F of x is equals to some leading coefficient times x minus a factor times x minus, well, not a factor, but minus a constant times x minus another constant, all the way down to however many constant factors there are. Well, C1, C2, all the way through Cn are complex numbers, and this includes real and not necessarily distinct, okay? Try to think about this for a minute, try to understand what we just said here, okay? It just means that you can rewrite it in such a way that it is a product of a bunch of x minus some number, okay? It could be an imaginary complex number or just simply a real number. Here is a different type of problem that you could encounter. So we were being asked to find the fourth degree polynomial function that has real coefficients and also has -2, +2, and I as the zeros of that polynomial, such that when you plug in 3 is equals to -150. So what are we being asked to do is to build this polynomial all together. So we know that it has 4 roots possibly, because it's a fourth degree polynomial. So how do we do it? Well, what we want to do, and the easiest thing to do, is to just build it up this following way. So f of x is equals to, well, x minus -2, which becomes +2. And before I even go that far, just know that there's a number in front of here. We're going to have to find that number in just 1 second. So x plus 2, which comes from this right here, and then x minus 2, which is this guy right here, and then x minus I, which is this guy right here. And remember what we talked about in the properties of the roots, that whenever you have a complex number as a root, then its complex conjugate is also part of that. Therefore, x plus I is also a root. And now we have 4 different zeros, so we can count them. Here's power 1, power 1, power 1, power 1. And if I add up all of the different terms, or the powers of the terms, we get 4, which is the degree that we were looking for. Okay, so let me kind of erase those little ones from up there. And they're not coming off. Okay, so now that we've done that, we have kind of like the backbone of our polynomial. Now we have to figure out this leading coefficient. How do we figure out the leading coefficient? We do that by using that last piece of information, which is the initial condition, right? This is called an initial condition. It tells me that whenever I plug in the value x equals 3, the outcome is going to be -150 in this particular case. So what does that mean? So -150 is equals to a times 3 plus 2 times 3 minus 2 times 3 minus I times 3 plus I. So definitely we can do this by hand, or just go ahead and do it in the calculator. Okay, so here we have 5 times 1, And if you remember multiplying complex numbers or complex conjugates, all you have to do is, in this very particular case, square the a's and the b's, right? So 3 squared plus 1 squared. And that's going to be 5 times 10, right? 3 squared is 9 plus 1 squared, so 10. So remember, this is all equals to 150, negative 150. So a times 50, and therefore a is going to be equal to negative 3. Once we figure that value out, we can go back and plug it in and have a more complete version of our polynomial. Okay, so this is a linear factorization form of the polynomial. We could and we should expand it out and see what we get. Okay, so we can do like negative 3 and then multiply whatever is inside of this parentheses to just get the actual polynomial in standard polynomial form. So we'll have x squared, and then notice how there is different signs in the middle. Then those terms are going to cancel out. You're going to get plus 2x minus 2x minus 4. And then same thing here, you get x squared. The way I'm doing this, I'm multiplying these two first, and then multiplying those two first. Okay, and then, negative ix plus ix, and then we'll have plus I squared. And then let's keep simplifying. We'll get x squared minus 4 times x squared minus 1. Here we'll have to do foiling, or double distribution, however you want to call it. So x squared times x squared is going to be x to the 4th power minus x squared minus 4x squared plus 4. And then if I distribute that negative 3, we'll get negative 3 x to the 4th plus, oops, actually before I even do that, I want to combine like terms. So x to the 4th, and this right here is negative 5x squared plus 4. And then finally, I am going to distribute the 3 and this will be our polynomial. So notice the difference, right? This and this are the same thing. They are just in different forms, right? One of them is a linear factor form of it. The other one is just a polynomial. And this polynomial has degree 4 with zeros, negative 2, 2, I, and negative I. Now let's talk about Descartes' rule of signs. And this rule is going to provide us with specific information about the number and type of zeros that a polynomial can have. So we could have positive or negative or imaginary type of zeros, like we talked about at the beginning of the video. But Descartes' rule of signs is going to tell us whether we're going to have a certain number of possibilities. So it doesn't give you an exact number per se, it gives you cases of possibilities. So the rule is based on considering the variations in signs between the consecutive coefficients. So what does that mean? So let's look at this example. We have the function here f of x, and we're going to count the change in sign from term to term, and that's going to help us determine how many positive zeros we're going to have. So let's look at this and start from 2x to the power 9. Well, that's positive, right? So it goes from positive to a negative. That counts as one sign change. Negative to negative, that counts as no sign change because it stays the same. Then from negative to a positive, that is considered one sign change. Positive to negative, that is considered another sign change. And from negative to positive, that is one sign change. So we write down that we can have 4 possible positive zeros. Now, why is it the positive ones? Well, whenever you start the problem, you're going to just use the original polynomial without making any changes to it, and that's how you find the positive zeros of it. Now, the rule also says that minus a positive even number, so that means take away 2 from the number of possibilities. So 4 minus 2 is 2. So there's also 2 possible positive zeros. Well, I can still take away another 2. So that means that if I take 2 away from 2, I'm going to have 0 possible positive zeros. What does that mean? That you could have a case where you have 4 possible zeros. You could have 2 or you could have 0. So in other words, you're looking at this as if it was different cases. Case 1, case 2, and case 3. After this, we're going to talk about how to figure out the negative zeros of it and the other possibilities. Here's the rule in more detail. So think of the regular definition of a polynomial that we've been talking about, like this, and it has real coefficients. So part 1 of the rule of signs, it says that the number of real positive zeros, or the rule here, is either the same number of sign changes like we just did, or, here's a big piece of that, or less than a number of sign changes by a positive even integer. So we'll get more into that in just one second. And if f of x has only one sign change, then f has exactly one positive real zero, meaning that if you only have one sign change, you can't do this part where you take away a positive even integer from the total number. Okay. Part 2 of the rule of signs says the number of negative real zeros of f is either the same number or the same as the number of sign changes of f evaluated at negative x. So you have to plug in negative x into the function f to determine the negative zeros. And as with part 1, the big or less than the number of sign changes of f at negative x by a positive even integer. So you have to take away a positive even integer from the previous number that you found up here to determine the different cases. Obviously, same as before, then the function f has exactly one negative real solution if and only if you only found one in the original count of sign changes. So it's very complicated in some way here reading the definition, So let's do an example and flesh it out. So let's determine the possible number of zeros, positive and negative, of this polynomial. Okay, so we'll make a note here that we're looking for the positive zeros. So positive zeros. And I'm just going to write the polynomial as it is. So x to the third plus 2x squared plus 5x plus 4. So let's start counting. The number in front of the x cubed is a positive 1. So from here to here, there is no sign change. From here to here, from positive to positive, no sign change. From positive to a positive, 0 sign changes. So altogether, we have 0 possible positive zeros. Okay? In order to find the negative zeros, we have to do f evaluated at negative x, meaning that everywhere there is an x, plug in negative x. And once that's done and simplified, we will count the different number of zeros, or I'm sorry, the different sign changes, and that's going to give us the possible negative zeros. So negative x to the power 3 is just negative x to the power 3, and then negative x to the power 2 is just x squared. Negative times a negative is positive. Then this is negative 5x, and this is positive 4. So let's go ahead and do the sign counts. From a negative to a positive, we have 1. From positive to a negative, we have another sign change. And then from negative to positive, we have another sign change. So all in all, we have 3 possible negative zeros. But then the rule says to take away a positive even integer. So what it means is to subtract 2 from it, and we get a 1. So that means that there are 2 cases for this. And I'm going to write it out in a table so that it makes more sense. So I'll say the number of positive zeros is either 0, because that's the only possibility that we found. Negative zeros, we found 2 possibilities, meaning that there is either 3 of them or 1 of them, because we have to take away the even number of zeros. So what it means is that there are 2 cases to consider. Okay, so case 1 and case 2, where there is either 0 positive zeros and 3 negative zeros, or 0 positive zeros and 1 negative zero. What the definition doesn't tell us to do is to look for complex zeros. That means imaginary or just complex in general. So this is where I'm going to tie in all of the information and kind of do a nice summary of things. So we talked about the fundamental theorem of algebra, and also some property before that said, well, if the polynomial has at most power n, then it has n roots. So what happens here in the case where there are 3 negative zeros and 0 positive zeros, right? That takes care of the 3 zeros that we were expecting. So it must be the case that there are 0 complex zeros. Okay, because all of the roots, all of the zeros have to add up to n, which is the highest power. Now, what happens here when there's only one negative zero and only, well, a 0 positive zero? Well, there's still 2 roots missing, and those roots have to be complex in order to justify the rule that there is going to be 3 different zeros. So let me tell you what's going on graphically. So you have a power 3 function. So let me copy the same polynomial, and I'm going to make a rough sketch of it, right? So we have something like this. Oops. And by the rules of algebra that we talked about in the beginning sections, the graphing of polynomials, then we know that this polynomial has a leg that's going downwards this way and a leg that's rising upwards on the right. We don't know what's going on in the middle, but we can assume right now. I don't want to get into too many details to the graph, but I'm going to say, well, what if this is the case where it goes like this? Okay, where it touches once and it goes up like this. So if we kind of go back to our probability, the different cases, here is one negative root or 0 and 0 positives, but this curve right here, this right here is kind of what determines the other zeros, the complex zeros. Okay, so the graph would look like this if this is the case that it's true. Okay, one negative 0, 2 complex zeros. But what if it was this one right here? Case number 1. What would the graph look like? Well, the graph is going to look like the following if it is the case. So it would have 3 negative zeros, meaning 1, 2, and 3. Okay, maybe not so going through the 0. Something like that, right? And it crosses 1, 2, and 3 different places on the negative side, right? So 3 times it crosses the x-axis, therefore there would be 0 complex roots and obviously 3 negative roots. Okay, so that's really what's going on graphically, and that helps us determine this, right? So obviously we're putting in together many different pieces of information, like, okay, I know it's a power 3, I know the graph is going to look like this. I'm using the different cases to kind of come up with a graph of it. Obviously, we can come up with something better by using the properties of graphing that we talked about before, like figuring out the y-intercept and so on. So that's another piece of information that we can use, okay, in order to come up with the graph of it and make better decision as to, okay, which zeros should I even consider? Okay, notice how here there is 0 positive zeros. Well, I'm not going to waste my time doing synthetic division by positive zeros if none of them are considered a possible solution, okay? I'm going to spend my time trying negative numbers to divide into the polynomial to then get a zero remainder, okay? That's going to be more fruitful since I am using some rules that kind of help me narrow down which ones are the zeros that are going to work. And with that, I'm going to end the lesson here. Thank you for watching.